Good afternoon, this is Mr. Schweitzer, and this is a short video on how do you know if a reaction is in fact a redox reaction. I'm going to hit the review button here. So we have a redox reaction. What does that mean? Well, redox stands for oxidation reduction. The old days, oxidation literally meant to gain oxygen, and reduction meant to lose oxygen. These particular definitions still work for some reactions. I mean, it's not false, but we've updated the name, the definition of the name, oxidation, and we haven't changed the name. So that makes the definition somewhat misleading. So it turns out it is to lose electrons, oxidize, and this means to gain electrons, reduce. So anytime you have a situation where there is going to be a transfer of electrons from one item to another item. Now, whenever we have a transfer of electrons, we have a transfer of charge. So we're going to see charges changing. That is the big deal here. Charges changing. Alright, so the goal here is to say, okay, is a reaction a redox reaction? Basically, we'll take our reactants and we'll assess, our charges, and then we'll look at our products and we'll say, okay, well, what are the charges on these guys? And we do know that the total quantity of positive and negative is going to be the same on each side, but are the individual pieces changing charges? Now, so what we're going to do here is we're going to add on this little worksheet here, which is in your workbook likely, and so it says, okay, well, what we're going to do is we're going to take our reactants and we're going to apply a handful of rules to them to see if what the charges are. Now, if you have, let's say, a copper atom, let's say Cu plus 2, it's easy to see this atom has a charge of plus 2. But if you have an atom or a molecule, let's say like water, H2O, the whole thing is neutral. So how do we know if this particular item is going to be having any charges changing? So we have this item called an oxidation state. And I sometimes call them mini charges. And it's the mini charge on each individual piece. So we'll take and follow some rules that assign charges to each individual piece. And these rules are given here, and you simply follow the rules. Oxygen is a -2, and there are some exceptions. We could have a peroxide, for example, which then it would be a positive, a -1. Hydrides are +1. Again, there are exceptions to that as well. Ionic compounds, whatever their charges are, is what their oxidation states are. It's stated nicely right there. And another one, all oxidation states must equal the overall charge. A couple of things you might see other places is where they might say elements equal 0. Well, it depends how you define element. This is just one element, copper. It has a +2 charge. So all the charges have to add up to the overall charge. The overall charge is +2, so therefore the oxidation state of this guy is +2. But if I have oxygen, O2 is the standard state. There's no charge there, so the only charge oxygen has nothing, just 0. So elements in their elemental state are generally neutral, and therefore they have no charge. Occasionally you'll see rules where it says also halogens are -1. That is another one which we may see. Alright, so I'm just going to go through a couple of these here. I have, let's say, CH4. So I'm just going to grab some of these, and you have your own workbook as well. Carbon is going to be, okay, so now hydrogen by rule is +1. Okay, now I have two numbers I put here. First one is the actual answer right here. That's what we want. Then up top here, I put what's called for office use only. That's for our little bookkeeping. I do know that all the charges have to equal the overall charge, which in this case is 0. So +1 times 4 is a +4. Again, +4 is not the answer. +1 is the answer, but it allows me to say, okay, well, if this is a +4 overall, then carbon must be a -4 in order to get a 0. And therefore, carbon's individual charge is -4, because there's one of them. And these are my oxidation states. Another one here might be, okay, let's go with Na2CrO4. Now, in this case, I have Na2CrO4. This is an ionic compound right here, okay, where this is a cation +1. And this is the anion, which is going to be chromate. It's going to have, whole thing is going to have a charge of -2. So I can either deal with this all together as one piece, or I can say the Na is +1, and then the chromate Cr4 together is a -2. So I can now deal with it separately. This is now done, and just the chromate. Oxygen is -2. There are 4 of them for a -8, and therefore, in order to get a -2 charge, the chromium has to be +6, and these are +6 right here, and then this is my oxygen states, and this is my oxidation states. If I left it together on here, then give myself a little room here. 2 would be a +2, -2 for a -6, sorry, -8, and then +6 gives me 0. So, again, just going through assigning your rules, you need a little practice at that. Make sure you see your teacher if you need more practice, and check your answers on some of those, because it's just a matter of following the rules. Now, down here I have several problems, and the goal here is to assign oxidation states, determine if it's an oxidation reduction reaction. Alright, so here I have iron, which is a no charge element, oxygen no charge element, and this is an ionic compound +3 -2. I know these because I just uncrisscrossed it. So this, is it a redox reaction? Yes, it's a redox reaction. Who's being oxidized and who is being reduced? Remember, oxidation means Leo, lose electrons, oxidize. Reduce means who's gain electrons, reduce. This guy is getting more negative, this guy's getting less negative, or it's getting positive. So the Fe is going from Fe to Fe +3. So is Fe gaining electrons? Is it gaining negative? No. It's losing negative. It's being oxidized. And therefore, if this guy is losing negative, then the oxygen has to be gaining it. And yes, it is. Reduced. Alright. In this case, for silver nitrate, in this one here, silver is a +1. Oxygen's a -2. Times 3 is a -6. Give me a +5. Again, I could have broke this nitrate out and done it all by itself, NO3 -1. So, and I would get the same thing, -2 and +5. That being said, this nitrate has to be +5, -2, and this is plus 1. The nitrate didn't change, so the oxygen states should be the same on both sides. Ionic charges plus 1, minus 1, plus 1, minus 1. And if you notice, all my charges are the same. This is not redox. Okay. Lost a few there. Okay. Let's try another one. Number 14. 14 is, I'm going to rewrite here, Cu plus AgNO3 goes to Ag plus CuNO3 2. Alright. Elements are 0. And this is a ionic compound, so plus 1, plus 2, because of the 2 there. And then the nitrate, of course, we did before. It was a plus 5 and a minus 2, but we'll see it again. Minus 2 times 3 is minus 6. A minus 6 and a positive 1 is a plus 5. And we'll get the same thing here. So is it a redox reaction? Yes. Okay. Who's being oxidized? Well, the copper is going from a 0 to a plus 2. Is it gaining negative? No, it's getting positive. So it's losing electrons oxidized. This guy is going from a plus 1 to a 0. So it's gains negative. This guy is being reduced. Alright, and other examples there for you to try. And the big question here is a reaction a redox reaction? And that is our big objective here. And once you have that, the question is who's being oxidized, who's being reduced? Thank you.